warm welcome to everyone. It's a privilege and a pleasure to be doing this webinar. I sincerely hope you will walk away from this webinar with a lot more confidence in using neural networks as well as these new age machine learning algorithms for credit risk modeling, which are now fully explainable and transparent and so on. So before I get started, a bit of housekeeping. Now, given that there are a lot of participants, muted everybody just to sort of we get through the presentation first, and we'll then have a question and answer session after about 30 minutes. And I would like the questions to be, please, if you could type it on the chat window, and I will go through every one of them, hopefully. That makes the logistics easier, and so that we don't have people talking over each other, and I can answer the questions to satisfaction. So with that said, let's just get started. These are exciting times for credit risk modeling, modeling in general, especially for the banks, where we will, where we look forward to having sharper tools to capture credit risk accurately, so that people who are underserved can be served better, and your prime customers can be served even better in terms of the credit products that we make available at the right price and at the right customer experience. Okay. So with that, let's go to what we'll be covering in this webinar. So while there's the focus is on the methodologies, there are some general considerations in model development, especially for financial institutions, that are overarching. Those never change. Those are given. And all the algorithmic improvements and enhancements are within that ambit of what needs to be addressed in building credit risk models, be it for underwriting or for collections or for credit line management and so on. So I'll be covering first key considerations in any model development. This pretty much holds across the board. Then I'll talk through these advancements that have happened in the last few years, which are now seeing the light of the day in lending institutions in terms of machine learning, the tools and techniques. Then we'll focus a little bit more specifically on credit risk modeling, and then we'll get to the part that we've been waiting for, how neural network itself can be applied and why it's explainable and so on. I'm unfortunately in a webinar like this, I can't get feedback whether I'm going too fast, too slow, but hopefully in the Q&A or any time in the chat, please feel free to, type out, hey, could you revisit that slide, or could you, not rush through this stuff and so on. Yeah, so with that, let's go to the key considerations in model development for a bank or a lending institution. So these things sort of never change. While there's a lot of excitement about the methodologies and technologies and so on, ultimately the models are only as good as the data on which they're developed. And the data ought to reflect the business process and the business problem that is sought to be addressed. So it sounds commonsensical at the outset, but you'd be surprised how little effort goes in. And this is something that we stress a lot in Scienaptic. Basically, it's important, obviously, to understand the process behind the business problem. What I mean is, if you're underwriting customers, it's basically important to know which channel these customers are coming through. Are they applying online? Are they applying through some mobile app? Or are these customers, applicants, being sourced through third party, like perhaps in the US, people would be familiar with the things like Credit Karma, where now people can check their credit scores, and then probably Credit Karma then sources these applications to the lending institutions, right? Each process then dictates what data would be available and whether the features reflect that accurately. Basically things like if someone's income doesn't pass the cutoff for affordability or responsible lending criteria, no point having those data points, if you will, in the modeling exercise. It would just confuse the algorithm. So it's very important to understand the process behind the business problem that's being addressed. And the problem needs to be broken down to component parts, and I'll talk about it in detail in the next illustrative slide that I have. And there's a temptation to model everything, but what I've personally found, and we find in our engagements with various banks, that it's very important to first go after the components that would provide the highest impact. For example, if we are trying to model for the expected revenue from a credit card customer, the biggest drivers are finance charges and interchange revenue on the sale transactions. Modeling for edge cases is not the most priority stuff, right? So that's the important consideration to remember. And that relates to also speed to market and ease of deployment. So speed to market, very important, because it's important to have a sharper tool working today so that you don't leave money on the table than to build the perfect solution 6 months down the line. Be it from what kind of data sources you'll have, or from what kind of algorithms you'll deploy, and so on. It's the speed to market consideration should trump, because every time we have a sharper instrument, it's important that such a solution gets deployed, because that's money on the table that we are not leaving. And it's exciting that now we live in a time where model development to deployment can actually be done in a matter of minutes because of the deployment platforms that have come of age. One I would definitely call out is our own deployment platform, the Ether Credit Underwriting Engine. But having said that, the machine learning algorithms are not that hard to deploy anymore, and the infrastructure is rapidly catching up across institutions. Finally, the exploratory data analysis, while it's not the most cool work that the data scientists perform, again, that goes back to making sure the data reflects the business process understanding. So without much belaboring these points, because these things hold irrespective of what technology or algorithms we use. So I just wanted to make sure, first of all, I convey these, and these things do not change, no matter how much the technology and the algorithms change. So here's a rather busy slide, but deliberately so, to sort of give a flavor for the complexity involved in modeling different things, right? For example, let us say we wanted to predict what would be the expected revenue from a customer applying for a credit card. If we approve that customer, what's the expected revenue from the card customer, right? Now, the customer itself, the applicant at that point, could come from different channel. We may have pre-screened that applicant and say, hey, please apply, and we would approve. It's also called pre-approved, and then in the US parlance. Then we may have sent a direct mailer saying, like, here are the cool benefits of the credit card. Please apply, and this is the expected. You may get the APR of anywhere from $14.99 to $24.99 or so on, like things like that. What's called an invitation to apply channel, and people apply on their own online through a browser or through a mobile phone, or sometimes over a telephone also. So now, once they apply, they could be applying with a balance transfer request, which means the credit limit that we will assign post-approval has to be at least as much as the request for the balance transfer. Because if not, then there's no revenue. Even though you approved the card, the customer does not take up or activate the card. Now, if someone does take up the card, the person could be surfing for what's called a balance transfer surfer or a BT surfer, meaning they transfer their balance from one card offer to another and so on. So there's very little expectation of revenue. Or someone could take up the card purely for balance transfer and do nothing other than just pay down the balance transfer and so on, right? So the spend is sort of constrained by the balance that is coming in due to the balance transfer process. Now, so this on the other hand, an applicant could apply without a balance transfer request if your limit is not appropriate the customer's needs, may not activate the card, but the person does activate, the limit is appropriate. You know, we would need to model for whether someone is a revolver or a transactor, and you know, if it's a revolver and also a high spender, you expect a high revenue. So this ties back to what I spoke about in terms of knowing the business process and what components you would want to take up to model for. And at Scienaptic, we do this very well. We do this for a living, if I may say so myself. So when we model, whether we when we employ neural network, we're not directly modeling for a customer profitability, which is like boiling the ocean. One almost never does that. One models for expected activation, one models for expected spend, and therefore what the likely interchange revenues is going to be, what's the likely revolve rate, and therefore that's going to drive the expected finance charges, and all of that needs to be optimized for what's the credit limit you would assign. So even before one even decides to use a certain algorithm, knowing the business process actually is really the provides a lot of bang for the buck in terms of the modeling effort. So that's in terms of, I just wanted to give a flavor of the complexities involved in a what you otherwise think, hey, it's a credit card, how hard could it be? And that's why I just want to give a flavor on the various components that drive the expected revenue, including, and all of them of course drive a customer's experience itself, because the line you assign has to be appropriate. The rewards or the offers ought to be opposite to the customer's needs. So with that, we'll move on to the advancements around machine learning tools and techniques that are relevant for banks, and why there's so much excitement now. I've deliberately titled this Beyond Logistic Regression and SAS. Many of us who have worked in or work in financial institutions have used logistic regression for the longest time. Logistic regression has served us well, helps us build very robust models, and that's a theme I would keep coming back to, because it's, while we want models to provide a very high lift, very high predictive power, by the end of the day, we like models to have provide repeatable results, be robust as much as possible, post deployment. And logistic regression has served that well, especially when built by analytic teams who have a lot of experience in this area. There's a lot of industrial scale process that goes into building the logistic regression models, or what's also called scorecards, if it's done in that way. Because there's a lot of effort that goes into data manipulation in terms of missing value treatment, outlier capping, multivariate, multicollinearity based variable reduction, and so on, so that the models will be extremely stable. Every organization have their thresholds or benchmarks around what feature would be allowed in a model in terms of maybe p-value, in terms of overall, each variable's what's called a variance inflation factor that controls for multicollinearity. So a lot of effort goes into this modeling, to make sure the model not only outperforms or at least performs to the required predictive accuracy, but more importantly provides repeatable results over time. Now, fundamentally, while Logistic has served us well, this process sort of handicaps, and the algorithm itself is handicapped by its linear additive form. I promise I won't be too technical other than a couple of slides, but that the additive nature of this model imposes what sort of functional forms it can actually model well for, and the fact that the logistic regression is very sensitive, at least directionally, to multicollinearity. In other words, the parameter estimates have to be have a tight standard error around them. So we have an instrument that was sharp compared to simple policy rules, but now we live at a time where we can have much more sharper tool without compromising on the robustness. So to satisfy this criteria of ability to model for more complex relationships without sacrificing robustness, really there are only a couple of algorithms that are in town which we found across industry that work very well, because these algorithms tend to be in technical language both low bias and low variance. GBM is one such methodology, gradient boosting machine, and this has been working well. It's probably the best off-the-shelf predictor, but one could go further and use neural networks to do even better, and you can have, and that's something I'll be talking about in detail. Neural network also helps you because it's a universal function approximator. You can capture much more nonlinear relationships, as well as use it as a tool for feature engineering and so on. The cousins of GBM, what's called random forest, also does provide robust results and better lift over logistic regression. But we've seen that GBMs from an ensemble perspective perform well, but neural network outperforms all of these because it has what is called a model capacity to capture more nonlinear relationships. But there are true relationships in the sense that they stay over time and therefore robust. Now, so most of us who spent many years in this area would have used SAS, but now and for a good reason, because SAS is a solid modeling platform and well tested. It's and all that, but that same sort of dependability and richness is now available in many other tools that are now available for free or as open source, or free for individual use but not free for enterprise, that sort of stuff. And all these tools have come of age. They now provide the same sort of rich functionality and dependability, or has always been the go-to in the academic world. And with the flavors of R like Revolution R, it also has the support of an organization behind it who would be able to take on any bugs and so on. Again, Python being a general purpose language is very powerful in terms of allowing data scientists, not just programmers, but data scientists to write really cool applications on top of the machine learning models. There are packages which have come of age like scikit-learn, as well as stats models for people who like to see the statistical flavor, including things like chi-squared and p-values of the estimates. H2O is another Silicon Valley based company that has brought together a lot of algorithms in a very computationally efficient manner. So they're state of the art. And Spark has been the original big data distributed computing paradigm, and and it has interface to R and Python, so that data scientists can leverage the power of Spark ML. Now, so there's obviously a bit of a confusion. So which open source or these kind of new age tools to use? Are they dependable and so on? They're all dependable. They serve different purposes, and so on. But what's really missing is the same kind of industrial grade rigorous process that we used to employ for logistic regression that resulted in robust models, right? And further, there's been the thing about these machine learning models are black boxes, and therefore they're not regulatory compliant. They're not fully transparent. There could be hidden biases and so on. And these criticisms were justified until maybe a couple of years back, but not really anymore, because now we have evolved a process that doesn't just simply throw in the algorithm, but create a process and a way of feature engineering and certain hyperparameter settings that make these machine learning models fully transparent and explainable, and also adverse action reasonable. Just for participants who may not be very familiar with adverse action reason, I'll just spend a minute on that. Basically, when an applicant, someone applies for say a credit card, and lending institution denies that application, it's considered an adverse action, and regulation dictates in most countries reasons be provided to the applicant why the credit application was denied. So it's not good enough to say, hey, your score was too low, or the probability of default was too high, because it doesn't leave the applicant any better, right? The applicant can't then say, okay, what can I do so that my score will be better? So regulation dictates that it's not enough to say just the probability of default is too high. You got to then lay out, give 3 reasons, 5 reasons, whatever will be the number, why that score was high, or the probability of default was high, or the inverse, the credit risk score was low. So until recently, at least neural networks couldn't do, but we figured out a way how to make neural networks also fully transparent and adverse action reasonable, and I will talk through that in subsequent slides. So moving on, this again, it's just this slide here is presents some more flavor to the explainability and regulatory concerns. They're no longer an issue. Privacy is no longer an issue because these tools can be deployed within the bank, and also the cloud has come of age. So this has got strong encryptions and data protections. So we are also seeing lending institutions migrating to the cloud. So the data privacy issues now no longer difficult to attain outside of the bank's firewalls because of the cloud solutions. And what cloud solutions also, and by the way, clouds can be also set up within the institution. What it allows for is scalability. Commodity hardware can be used to scale up the solutions rather rapidly. So the whole the IT cycle is largely compressed. In terms of regulation, as I'll be talking about it, discriminatory lending is no longer an issue with machine learning models. When built in the right way, they are fully transparent, and any hidden biases can be unearthed and therefore can be removed by changes in the modeling process. Then there's the I spoke about adverse action reasoning, and I've already alluded to the stability of models. So it's really the process that dictates how stable the machine learning models will be. There's a lot of good information, if I may say so myself. Our website Scienaptic has a couple of white papers on this for people who are a little bit more technically inclined. Can look at these white papers, and I'm very happy to take on questions around that. Okay, just a few thoughts on creditless modeling itself. It's about what are the considerations in creditless modeling. Ultimately, we want to reduce loss exposure. We want to be able to know what's the revenue, and we want to make sure we approve the right customers and make sure the product matches the customer's needs. Data, risk models, and policy rules constitute the three pillars. One might ask, why would you need policy rules while there are risk models? To sort of capture any emergent phenomena that may happen. And there are other rules, like very simple rules, like will not approve someone who's below the age of 18. Since we have never done that in the past, the institution would have never approved anyone below the age of 18. That wouldn't be part of the data. No algorithm would automatically know one should score an underage applicant low. So there's always some need for policy rules. There are other reasons. For example, if the income fails the affordability cutoff for a particular product, then no point spending money pulling data from bureau. So there are these upfront rules. There is a place for these. And then when the economic cycle turns, there may be a need to put in some additional rules, like no bankruptcies and so on, because in good times the default behavior of customers, even customers with past delinquency, may be very good, but when there's a recessionary cycle, it will tip the balance. So there'll be some time before the models can catch up. So that's why the policy rules. And there are several regulatory, but this is very US specific, but there are similar regulatory bodies and regulations that exist in other countries, and the models got to comply with that. So here's roughly a credit risk modeling design. I won't belabor too much, but algorithm itself need not decide what's the delinquency that one is going to model for. So it's important to choose the right vintages and the right bad definition. You want to choose to model for a bad definition that is severe enough that the cure rate is low, so that the model is not confused by sloppy payers, for example, who may have missed a payment, but because they forgot to set up auto debit, or it's just that they forgot and will pay a couple of days late. But so if that is marked, so even 1 day delinquency, if it's marked as a bad definition, the model will have a very hard time separating the really risky customers from lower risk customers. And the choice of data obviously plays a huge role. There's cost versus the risk mitigation trade-offs, but whenever it's it's always better to source more data than less. So we will move on. I had a couple of slides. Maybe we'll be able to revisit this later about reject inference and so on. So let's move to the part that we've been waiting for, explainable neural networks itself. Now, just a very brief overview. Neural network is proven. It is a universal function approximator, can model very complex relationship with sufficient number of hidden layers and nodes. Any function can be approximated to any given accuracy. all the recent hype has been because of the successful applications in image recognition, text and speech processing, and so on. But what's the beauty of neural network is it's not just one method. It's actually a suite of methods, like fully connected convolutional neural networks. This work very well for supervised learning. Then there is autoencoders that can be used for outlier detection. There is LSTMs for time series modeling. That's more relevant for the banks. And there are some optimization that can be done with reinforcement learning, and GANs have been getting some press on image enhancement and so on. Now, so that's one of the reasons why we chose neural network and how we could adopt it for credit risk models. Now, how do we make neural networks explainable? So this is a key slide. It's going to be a little bit technical. So if we throw in a continuous variable like, say, utilization on revolving trades, because of the quirks of the data and so on, it can show spuriously a complex relationship with the target definition, with the target, namely something like 90 days past due or something like that. So, but if we don't do that, people familiar with the scorecarding world, where you bin the variables, then what you do is, while you increase the degrees of freedom, you end up, instead of modeling for a continuous variable, you discretize all the continuous numerical variables. Then what we will have is, like, let's say we have m features and we discretize each of them into n bins. Then you'll have at the max n power m combinations, right? And so no matter how complex the neural network model itself is in terms of hidden layers and number of nodes and so on, you get a finite mapping, first of all, from these bin combinations to the predicted probabilities. And therefore, at each bin, you'll be able to know the predicted versus actual, what's the bad distribution, and so on. And therefore, you will be able to know, if given a score cutoff, what is the expected approval rate at each feature bin level. And that is the crux of how we make neural networks explainable. And we have a modeling workbench which helps do this very seamlessly. And so this is really the most important reason. Like, for categorical variables, they're already discretized, but when we bin the numeric variables and we get to control what pattern, including imposing monotonicity, that then makes the neural network fully explainable. And there's one other feature of binning which makes neural network a very ideal choice, is it can learn features themselves. So here there is a, think about a simple ratio like utilization on a credit card. Now, if utilization of credit cards, nothing more than balance divided by the credit limit. So a ratio like x1 divided by x2. If x1 and x2 are sufficiently binned, then the connection, since there is connections between these two input features, you can actually learn the entire ratio, so long as the values in x1 is a little technical, so long as the x1 and x2 are bounded, which in practice it is. Nobody has a $1 million credit line or something like that. A credit limit is, for a credit card, would in the US may range from $500 to $20,000. It's still well bounded, and balance is already bounded by this thing. Because in real life, continuous variables are actually bounded, and they can be binned, and a finite number of connections can be formed. Even a variable like ratio can be learned very easily, and this is a very telling feature, because a feature like utilization is easy to learn, but a more complex ratio like say there's a joint application for a loan, let us say, and you want to have a ratio variable like the debt burden of applicant 1 plus debt burden of applicant 2 divided by the income of applicant 1 plus income of applicant 2. Now that's a complex ratio. No tree-based technique can learn this very well, and it's sort of proven out in research. These kind of complex features can be naturally learned by neural networks, and that's another reason why we use neural networks largely to sort of discover features that we wouldn't have already hypothesized about. And one may get a feeling, no, I have to have very fine bins in each of these variables to get a ratio. But in practice, you are going to be using these features to further model the target definition, like bad definition, in which case actually the bins don't need to be that fine actually, and even 5% bins or larger bins pretty much works in practice. So this is the kind of the technical stuff that I do want to cover. This is what brings about neural networks explainability, this binning feature, and there's a way to do it, which is sort of proprietary how we do it. But fundamentally, this is the basic idea. So you would know, you'll be able to actually see things like what we have here. Let us say this is from publicly available data. It's called German credit data. That's so this in this data set, these are like applicants who applied for a personal loan, and that anonymized 1,000 record data set is available publicly. So requested duration of the loan is one such feature. So here the duration is binned and monotonized. People familiar with scorecarding would know how the monotonization process works. But basically the bars here are the volumes that fall into each of these bins, and the lines are the bad rates. In this particular case, the actual bad rate is the black line and the predicted bad rate is the red line. Because duration is has been binned, it does not matter. It could have been a continuous variable. So the feature in the model will only fall in this finite number of buckets. In this particular case, 6 buckets. So we know exactly what's the average predicted bad rate there is and what's the actual bad rate is. One, we can do model performance comparisons, but more importantly, those average predicted bad rates provide what's called a marginal contribution, and this makes it fully explainable, because no matter how complex the variable model is, at a bin level, we know the exact distribution of the predicted bad rate. Here we just shown a red line, which is the average predicted bad rate, but we can actually have box plots. We will know exactly what's the distribution at each bin level, and that helps us tell what's the probability if someone, for example, requested a loan for of say 20 months. What would be the likelihood the person will be approved given a score cutoff? So this can be done and this is a screenshot from our bespoke tool. We can do this for each variable. So why is this important? Now that we know how this binning helps in making the model fully transparent, therefore, how do we then use it for adverse action reasoning? The trick is really, say, let's take the top left graph here, the total number of inquiries. It's a standard credit bureau variable. So the median customer, the representative customer, may fall in this bucket, and therefore the marginal contribution for that particular bucket, because that the model predicts, is say 0.06. And this is illustrative, but a real example from a real data set. And let us say our particular applicant had 4 inquiries. Say the representative customer had only 0 inquiries, but this particular applicant had, let's say 4 inquiries. This falls in this bucket. The marginal contribution probability that model predicts is 0.19. So the applicant is worse off on this dimension by minus 0.13. And the same process here, the representative customer had a utilization that was between 1.5% and 50%. And this particular applicant may have had utilization on revolving trades very high. Again, the difference between the two marginal contributions is minus 0.08 and so on. And in the number of revolving trade lines, this particular applicant is actually better risk on an average compared to the representative customer, because the median customer had 3 revolving trade lines and this customer had more than 8, probably 10 and so on. And so therefore in adverse action reasoning, we know the inquiries drove down the score the most, followed by months since the recent collection feature, followed by the utilization. So that's the order. So not only are we able to generate adverse action reasons, but we can give it in the order of what caused the largest fall and what caused the next largest fall in the score, and so on. So the customer also comes off from the adverse action interaction better off knowing, okay, well, if I had not sought that much credit by having too many inquiries, my score would have been higher, and maybe the customer would pass for a couple of months before applying for credit again. So this leads to much less customer complaints, and it's anyway regulatory important. So this general framework is applicable to our way of doing neural networks, because the models, all features are bin. There is this kind of verbiage like too many inquiries or recent collection items can be actually given, and they are English language understandable, and it's fully regulatory compliant. So I'm breezing through a lot of these. It's a sort of a lot of stuff, but I'm hoping we can cover some of the doubts in the question answer session. Now I'll stop at that. If I were to sort of summarize, the explainability comes naturally, irrespective of how complex the layer is and the hidden layers are, by discretizing the independent variables, or what's also called features. Not only do we discretize as a way to monotonize, if that's what makes intuitive sense, and then the models itself is built to high level of accuracy. Neural network allows many more features to be in the model than a traditional logistic regression, because the weights adjust themselves so that the standard error doesn't blow up. And finally, because of this finite space mapping at each feature level, we know exactly how the model is behaving, and therefore we can do adverse action reasons. In fact, adverse action reasons, the verbiage can be set at not at overall feature level, but we can actually set it at a feature bin level, so that there's a richness of adverse action verbiage, and lot less customer complaints and lot less operational risk in using these models. So I hope I have given you a flavor of why neural network is not a black box and can be used in credit risk modeling. So I will take questions and I'll answer them in the order I'm receiving the questions. So there's a question here which says, can you share a bit more about how neural network models are explainable? Is it just sensitivity analysis? No, okay. So I hope that binning and this adverse actioning sort of answers that. It's not just sensitivity analysis. It is in a sense, but it's actually quite it's an exact analysis, because we know the exact distribution of marginal contribution probabilities for each feature bucket. I hope that answers your question. If not, please feel free to ask a follow-on. Okay, I think maybe I'll just unmute the participant. I think it's probably easier to just ask the question rather than type out the question. Okay, yeah, the floor is open for questions. Thank you.
Hi, Subbu. This is Uday Soni from Linopsys. I asked that first question that you answered. Yeah, I think it's pretty much clear. I still have a little bit of a doubt around usually explaining it in these simple terms. Is it always possible, or have you ever found it to be difficult with some models because they are highly interactive models or nonlinear models, where combinations of interaction effects are at play?
Maybe there are more questions on this particular technical slide that I can talk about. Well, if you're, just still thinking through the questions, I can go to some of the slides I skipped on some of the principles of credit risk modeling itself, and then, at any time, please type out the questions on the chat window.
Hey, Subbu, can you hear me?
Okay, in models, it's a sort of illustrative example. Again, I wanted to stress that the need for reject inferencing does not go away with neural networks, or for that matter, any machine learning methodology, because the model is only as good as the data it's built on. And if the model is built purely on approved customers, it will not capture certain dynamics that will be there in the through the door application population. For example, if the bank has had a policy of never approving anybody with delinquency in the last 12 months, so such a model, the model itself would know nothing about delinquency. So it's very important that the models are built including the declined accounts, and these machine learning models are no different from the traditional logistic in the sense that it naturally allows for reject inferencing, and those the same principles of how we do reject inferencing still holds. Perhaps building a known good bad model and then scoring the decline population or reweighting them and so on. We have some proprietary techniques, but some of the techniques are well known, including augmentation and so on. Just to reinforce why reject inference is important, if the applicants fall in if let us say this is the risk spectrum, if you will, the decision boundaries at the margin. So in benign cycle, economic cycle, probably the thresholds are lower, because in a benign cycle, even higher risk customers tend to have fewer defaults. But in a recessionary time, it needs to be moved up and so on. So so it's important the model works very well in that margin, and that's why we have a technique of overweighting around the margin. So that is done prior to the neural network modeling itself. So the model learns to be very sharp at the margin or at the operating region where the credit score have to be the sharpest. Okay, there's a question that I received. Can the explainable AI generate a story narrative that can be embedded in customer communication? So I think I spoke through that question very quickly. Just to for everybody's benefit, the question here is: can the explainable AI generate a narrative or a story that can be embedded in consumer communication? Okay. So the answer to that is absolutely. In fact, that's what the adverse action reasoning is about. It's not just about communicating the verbiage to the customer. The our platform once we set the verbiage and we can have the, we can apply principles of narrative science to actually tone up or tone down the way the messaging is done, and that by itself is not so much dependent on the neural network, but this way of building neural network makes it easy to generate that story precisely because we know exactly what is going on, and we in fact routinely do that. So these adverse actions reasons of the English language communication is not just for the customer, it's also for internal understanding of why customers get rejected, what's the majority reason why the customers get rejected, and so on, so that the banks can construct appropriate products or change their strategy and so on. So short answer, yes, our Ether platform hugely facilitates that communicability and auto narration, if you will. There's I hope that answers the question about communicability and automatic narration or story generation from the results. Now, there's another question here. It says, since we are talking about regulations and restrictions that don't show up in the data, how do you identify which ones need to be encoded manually in the model? Now, this binning technique automatically would be able to throw up any biases that may exist actually. You may say things like, if you were to throw in a variable, even though you don't want to use it in the model itself, but for your exploratory purposes, if you throw in a variable like gender or the region or so on, you would automatically know how the model is behaving across the two categories, which are two or more categories, if it's a gender variable and so on. So then one could know whether such biases exist inherently, and how it can be corrected is by making the bins more coarse, so that these bias effects get washed out because of averaging between bins. So that's an important part of the process. Our Ether modeling engine automatically provides ability to do these coarse classing before modeling in order to wash out that bias, so that the final model does not have that bias built in because of some historical quirk in the data. How much better is Ether compared to logistic regression models? Is another question I just received. We are consistently finding more than 15% lift in the 15% over logistic regressions case. In fact, when it comes to the bad capture rate, it's actually 20% plus, or its counterpart. We're able to, a large bank, we could drive up the approval rate if the model was implemented from 52% approval rate to 60%, which is a huge lift. So 15 to 20%, we are finding it across the board in terms of how much better this performs over logistic regression models. And okay, there's another question here. It says, okay, there are a couple of good questions now. First question is, what happens when the model sees customers that are unlike any it had seen before? New region, different age group, etc. Now, the general answer is, model is only as good as the data it's built on. However, neural network is uniquely placed to learn as the data comes in, right? So there's some time before the model will catch up. But unlike other model forms, neural network, just the weights have to be updated a little bit. And so there's what we call the feedback loop. So in fact, our platform allows for the performance data to be, the actual realized performance data to be fed back. And we have placeholders, because the model form allows for variables with completely missing values. We keep placeholders for variables that are likely to come in the future. So the network adjusts itself as the new performance data feeds in and new variables become available. So which will capture this new kind of data points. In fact, if anything, this is the modeling process is most amenable to learn as it goes. And this is a phenomenon we find in fraud modeling especially, and we've been very successful in that respect, because fraud is always an emergent phenomenon. Constantly the fraudsters are changing their tactics, and therefore the patterns change, new zip codes become more vulnerable, and so on. So I hope that answers the question about what happens when the model sees customers that are unlike it had seen before. In credit risk modeling, it's much less of a problem, because it's very unlikely unless you're entering a new market, and there are ways to fix it through anonymized peer data that you get from the bureau, because bureau is such a large repository of the credit eligible population. Now, there's another question. How do we know higher approvals don't translate into higher risk? In fact, that's exactly our model addresses. So we come up with because the model is better, the lift is better. For the same bad rate, you could approve more, or if you want to keep the approval rate the same, you will have much lower bad rate. So in fact, that we have proven with several leading financial institutions. So higher approvals do not translate into higher risk, because we have a sharper mousetrap, if you will, because logistic regression, so it's a blunter instrument. For your particular bad rate risk appetite, you can only approve so much more. But if you with a sharper instrument, you'll be able to discriminate at the margin better. So you can keep, for the same bad rate, you can have a higher approval rate. And this is actually a very large number. For example, a large bank, we were able to change the approval rate from 52% to 60%. That's a very 8% increase in approval rate, absolute number. This is very large, because the predictive power of the logistic regression in terms of KS was in the low 40s, whereas the predictive power of this model was in the high 50s. So higher approvals not only do not translate to higher risk because of this specifically advanced modeling technique, which provides sharper instrument. Okay, any final questions? We have unfortunately come to the end of the hour. Passingly, I would have preferred maybe the next webinar, a more interactive session. We got to work out how we can do this for a large group, but I would have really loved to have more interaction. But okay, there's one final question, and after that, in the interest of time, we'll close out. The question is, will neural network models be more likely to approve revolvers than transactors? Since they generate more revenue, how does this behavior differ from previous technology human decision makers? Okay. Well, will neural network models be more likely to approve revolvers than transactors? Not necessarily, not inherently. It is true, transactors tend to be lower risk, but not always. And so what banks look for is the sweet spot, revolvers who are also low risk. There's a complex phenomena. There could be customers who revolve on one card but are transact on the other card. There are all sorts of mental accounting people do. So neural network model is not inherently biased towards approving revolvers, but what it does well is to separate better the risk dimension of within revolvers and within transactors. So within transactors, it's able to risk grade better, and within revolvers is able to risk grade better, so that the institution can approve lower risk customers, irrespective of whether they're going to revolve or transact. And it's far more sharper than human decision, especially because unlike image recognition, credit default is a future event, so human doesn't really do any better than an algorithm. So an algorithm actually does much better than a human being. Whereas in things like recognizing a car, it's a point in time phenomena where the human's Bayesian error is actually rather low. So there the neural networks have to catch up with the human ability, which they have and have sort of exceeded nowadays. But when it comes to predicting a future event like a credit default, even logistic regression performs way better than judgmental underwriters. And of course, neural network performs even better than logistic regression. So I guess that brings us to end of the hour. Like I said, I thoroughly enjoyed the session, but I hope I could convey how we make this happen and why this is exciting, in terms of having a sharper instrument in the credit decisioning process. I would have liked it to be even more interactive, but the logistics, I guess, we would manage better next time around. But thanks a lot for joining this session. It was really a pleasure and a privilege. Thank you very much, and have a great day or a great evening.